Hello, hello. Today, quantum physics 13.1, the photon model. We are in the specification OCR A. This is just lessons here. We are going to be trying to explain as best as we can about quantum physics. For hopefully those maybe trying to use this as revision, or maybe those trying to better understand quantum physics. Now, for context, I am working with the OCR A textbook. I am using the textbook as my guide. So pretty much everything is going to be quoted from the textbook, just to make sure that I've got sort of things right. Right, starting off. What is a photon? If you can answer that already, that's good. So, in 1900, Max Planck, I think he was German, I don't quite remember. He discovered that electromagnetic radiation being light, gamma rays, X-rays, UV, radio, infrared, micro, the EM spectrum, electromagnetic radiation, exists in certain values. Now, what we mean by certain values? He said that they come in little packets of energy. Quote unquote, little packets of energy. Now, these little packets of energy have a value, however many joules of energy. That's the value. Now, each packet of energy is called quantum. Quantum meaning the smallest possible packet of energy. Now, if you have multiple or many of these little packets of energy, it's not called quantums. It becomes quanta. Quanta. You don't really need to know this quanta stuff. It's just a good bit of little knowledge just to know all that stuff, really. But yeah, so he discovered electromagnetic radiation it comes in little packets of energy. Einstein called them photons. I'm sure we've all heard of photons somewhere. Photons we quite often use them with light. Quite often say, light is photons. Light is part of the electromagnetic radiation spectrum, EM spectrum. So light is, in turn, photons. It's loads, millions and billions and God knows number of photons sort of forming a wave in a way. That's sort of what we're saying here, which we'll get into in a second. Right, good flashcard to make. A photon is the smallest packet of electromagnetic radiation. It is the quantum of electromagnetic radiation. Smallest packet could be rewritten as quantum. As said earlier, quantum is the smallest packet. So, good flashcard to have, extra knowledge. This proves that electromagnetic radiation has a particle nature. We just said that they are photons, there's all these little photons. These photons are particles. But we've established electromagnetic radiation is a wave. It travels through space at the speed of light. How are we now saying it's a particle when it's a wave? It does diffraction. Light diffracts, fringe separation. We've done that. But now we're saying it's a particle. This is quantum physics. It's very simple. Quantum physics is the study of how matter and energy behave, you need to think very small scales, where quantities exist in discrete values, tiny values, and show both wave and particle natures. Very important. Wave and particle. Eventually, in this quantum part, you will reach wave-particle duality. They can be the same thing, okay? We've just established that light is a wave, but light is also a photon, which is a particle. It's both. Quantum physics is the understanding of this, and it's learning about how it can be both. Particle nature when it is in contact with matter, when it hits something, but a wave nature when it's traveling through space. Quite interesting. Now, we've said that the photons are small packets of energy. How do we work out what the value of this energy is? We do it with this equation. E equals hf. Very simple. E, energy of the photon. This is what we're looking for. H is Planck's constant. Planck's constant is one that you will need to know. Planck's constant does not turn up in the data formula sheet for the exam. Planck's constant is a value that needs to be memorized. And frequency. F, nothing special about frequency. E is measured in joules, like normal, energy is measured in joules. H, Planck's constant. Planck's constant is 6.63 times 10 to the minus 34. Okay, very small number. Remember, we are dealing with quantum physics here, ridiculously tiny stuff. This is one that you will not get on your data and formula sheet. Memorize it. And then E equals HF. This does turn up on your data and formula sheet. E equals HF. However, it's always good to know it, sort of off by heart as well. Make them into flashcards. Very handy. Now, what do we know about F? F is the frequency. F turns up in the wave equation. C equals F lambda. Remember, C is the speed of light. It's the velocity. V equals F lambda. Remember, C equals F lambda. We can rearrange to get F. F equals C over lambda. We substitute that into this. Gives us E equals H times C over lambda. Then H over 1. That's what it sort of is equivalent to. Gives us E equals HC over lambda. This is also a very important equation. It is just a variation of E equals HF. Nothing too fancy. However, it is used readily throughout quantum physics because now we can use lambda, the wavelength, to work out the photon energy. We don't need the frequency. And if you notice, HC up here, they're both constants. So all you need to work out photon energy really is lambda and just memorize H and C. This is another important equation to know. Make it a flashcard. E equals HC over lambda. Now, to show you that this is actually a really simple equation, because like most equations, it's just plug in the numbers and you get your answer. We're going to show you, okay? We get a worked example, a red light with a wavelength of 633 nanometers, right? Calculate the energy of the photon. Well, we know that the energy of a photon is E equals HF, but we have, well, the wavelength. So, like this equation that we just learned with the wavelength, we know, because obviously we can use this wave equation and turn it into E equals HC over lambda. Now, all we need to know is H, C, and lambda, and we can get E. Well, we know that H is 6.63 times 10 to the minus 34. And we know that C is 3 times 10 to the 8. And we know lambda is 633 nanometers. So that's 633 times 10 to the negative 9 meters. Plug that all into a calculator, and you should just get 3.14 times 10 to the minus 19. As seen here. Remember, E is measured in joules, so it's joules of energy. That's it. Plug in the numbers into the equation and you're good to go. It's quite simple to understand, really, for the whole equation. It's not that difficult, really. It's like a normal equation. Now, if you notice, actually, you can see the size of this number right here. Notice that it's times 10 to the negative 19. That is a ridiculously tiny number. Very small, okay? We've got to question it. Questions of scale. Is it sensible to measure 3.14, was it, joules? No, 3.14 times 10 to the negative 19 joules. Is it sensible to measure that in joules? That is a tiny number. The answer is no, it's not sensible. Photons are incredibly tiny. The energy is really small. Using joules is not sensible. Context, as we just worked out in the example. Typical red photon, 3 times 10 to the minus 19 joules. That is not a lot. Okay, very simple. We use a different unit for energy. Still energy. Okay, it's still like the joule, but it's just like smaller, so it works better. Electron volt, EV. You need to know this. Electron volt. It's just a measurement of energy. That's all it is. It's just another way of doing it. It's pretty simple. This is slightly difficult to sort of figure out here now. The electron volt is defined as the energy transferred to or from an electron when it moves through a potential difference of 1 volt. Now, I didn't quite get this to begin with at first when I'm doing my lessons. It's just kind of confusing. It is very good to put this on a flashcard. They do sometimes. I've had a few questions where they ask me to define an electron volt. It's kind of weird, but then again, it's also quite easy to remember. It's the energy transferred from an electron when it goes through 1 volt of voltage, well, potential difference, you know? That's all it is. Flashcard this. Very good to remember that. Helps with your understanding as well, really. Now, the electron volt, the energy transferred to or from... Oh, yeah, I just said this. Flashcard it. Flashcard it. Using its definition, we can work out what an electron volt is. Now, from the previous topic... Well, not the previous topic, but previous topics, we know that work done equals voltage times charge. Work done is also energy transfer. We have also learnt this in a previous topic, okay? Energy transfer. What's the definition? The energy transferred from to or from an electron. Okay, there we go. That's perfect. Now, when it travels through 1 volt voltage, what do we also know that E is? Electron is? It's a charged particle. It has a charge. So this works really good for us, okay? It's W equals VQ, okay? We know that the voltage is 1 volt. It says the definition goes through the potential difference of 1 volt. And we also know that the charge of an electron is 1.6 times 10 to the negative 19. If this doesn't come up in your formula sheet, you could memorize this number. It's a number that you will need to know. It's very handy, really. But yeah, using that knowledge, we can then therefore say, well, it's W equals VQ. Well, V is 1, Q is 1.6 times 10 to the minus 19. Well, what do you know? 1 times the thing is the thing. So W is 1.6 times 10 to the minus 19 joules. What is this? This is the energy transfer. This is W. This is work done. This is the energy transferred from the electron. The definition is that the electron volt is the energy transferred from an electron when it goes through 1 volt. So this is the electron volt. 1.6 times 10 to the minus 19 joules is 1 electron volt. This is the electron volt. You need to know that. Now, it's very simple. 1 volt is 1 EV, 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. This, very handy to have on a flashcard as well. It's a bit somewhat awkward. I don't know why I find this one difficult. To go from electron volts to joules, okay, to go from that way is divide by 1.6 times 10 to the minus 19. If you want to go from joules to electron volts, you multiply. For some reason, I always forget that. That's why I'm saying you should write it down. But in all fairness, just do what you want. but I think very handy to know that. It's conversion, because remember, we've got E equals HF. But quite often, well, E, remember, is joules. But quite often in the question, they might ask you to give it in electron volts. Or they give you electron volts and expect you to use this equation, meaning you have to interchange from electron volts and joules, because the exam board is kind of annoying because they decided that you really need to know it, because you kind of do. That's why this is quite important. Moving on. Sort of going back to Planck's constant here. That was sort of a bit of the electron volt was a bit of a tangent, just to like establish the electron volt. Back to Planck's constant here. We can use LEDs and we can use LEDs to work out Planck's constant. This is a practical which you might do or might not, depending on your school. You need to know it. LEDs convert electrical energy into light energy. Light is electromagnetic radiation. Electromagnetic radiation, as we established, are photons. So it's a particle or a wave, but we're talking about particles here. That means they emit photons, visible photons, because we can see them. Red, green. You can see them, visible photons. Now, you need to know that LEDs only turn on at a specific voltage. This is something that you're supposed to, I think it's only triple science in GCSE. I didn't do it because I did combined, but I had to figure this one out on a later date. LEDs only turn on at a specific voltage. If you've got too small of a voltage, they will not turn on. They have to hit a specific voltage where they have enough energy to turn on. What's that called? That voltage is called the threshold voltage. Threshold turns up quite a bit in this quantum. It's just threshold voltage. It's just the voltage where the LED turns on. Know that. Now, why is this the case? Well, the LED, I got this little well over here. Imagine the photon is sort of sitting there. If you give it some voltage, it might jiggle up and down a bit. But it doesn't escape. You see, this is like the escape line. It needs to get out of that escape line. How do we do that? Well, you can keep giving it, and it might just reach it, but just doesn't just quite get out, right? But once you reach that threshold voltage, once you hit that specific amount, it will have enough energy to basically just pop out. And that we can see. We can see when it pops out. That's all it is. But then that popping out, just coming out, and then being able to see that threshold voltage means that voltage is equivalent to the energy of this photon that has just come out, because you've just given it, I don't know, let's say, you've given it 100 volts of energy, and that's its threshold voltage. It pops out, now it has 100 volts of energy at that point in time. It's the same as the energy of the photon. So we can use, because obviously we are putting the voltage into this photon, we can measure this voltage with a voltmeter. It's pretty simple. However, once we find the threshold voltage, we need to do all sorts of stuff to then be able to actually utilize it for the physics that we are doing. So this is confusing. Remember, we are trying to find Planck's constant here, okay? What is Planck's constant? Planck's constant is H. So back to this W equals VQ. Remember, threshold voltage. Threshold voltage means it's like the minimum voltage required for it to turn on. V0. V0 means threshold voltage. If you see F0, that means threshold frequency, the minimum frequency required. Okay, the 0 is just like the minimum value. Charge on an electron. Okay, and then remember, well, if you look, see, W is photon energy, threshold voltage, charge on electron. But this is photon energy. What do we also know that photon energy is? Photon energy is E equals FH. This E is photon energy. That means HF is photon energy. So we can substitute HF into this to give us HF equals VO times E. What's E? That is the charge on the electron. All confusing. Try to see the arrows. Okay. But then again, F is C over lambda. So we substitute that into the F there. H times C over lambda equals V, well, threshold voltage times the charge on the electron. So the sort of thing we get is H C lambda equals threshold voltage E. That's what we get. This is a sort of equation. You sort of need to learn this, how we get it. It's not that difficult to understand once you start to get the other things. So just need to practice it. It's not too bad. Now, to find Planck's constant, because it's a practical, we plot it on a graph. We need a y and an x-axis on the graph. V is the, well, VO is on the y. So VO is on the y. And 1 over lambda is on the x. Oh, we don't have 1 over, oh, we do. This is equivalent to 1 over lambda. Because it's, it's like above here. So in the end, we can sort of write that as H equals, no, H times C times 1 over lambda equals VOE. We normally write it as this form, but just to sort of show you this 1 over lambda, because I didn't get it, the teacher wasn't entirely the best at, he goes quite quick. I didn't quite realize what he was talking about. Yeah, this 1 over lambda comes from this, 1 over lambda, not too difficult. Y and the x-axis, try to keep that in mind, okay? Well, look at that. We're doing y equals mx plus c. That is the line equation. We said that y is the threshold voltage. X is 1 over lambda. Put that in. Y is here. X is 1 over lambda. That leaves us with the rest. HC over E. Oh God. HC over E. How do we have a HC over E? Well, if you remember, the equation we had was HC over lambda equals voltage, threshold voltage times the charge on the electron. We've now said that the voltage is the Y, so we need to get voltage on its own. So we need to divide by E here. No, I'm tripping. I'm getting confused here. Wait a second. VOE equals HC over lambda. Now, we also said that VOE equals H times C times 1 over lambda. We just did that just up here. This bit here. Here. Now, we can say that this is just this is sort of like I'm not really doing much. I'm just HC times 1 over lambda. And then what you do is you just divide by E on HC. So VO equals HC over E times 1 over lambda. Because this is the Y, this is the X. I don't think I've done that correctly, to be honest, but it works. You can figure it out. Y, X, M. There's no C because there's no plus, I don't think I've done this right. Don't look at that too much. But voila. What do we know that M is? M is the gradient. So if we know that the gradient is this, then we can rearrange that to get H. I can do this one. Gradient, multiply by E to get that off the bottom. Multiply by E, and then it leaves us with HC. Divide by C, boom, gives us gradient times E divided by C equals H. Now what's H? H is Planck's constant. What are we trying to look for? We're trying to look for Planck's constant. So if we plot a graph, get the gradient, multiply it by the charge on an electron, which is 1.6 times 10 to the negative 19, if you remember, and C, which is the speed of light, you can fuck out Planck's constant, which is what is part of the practical. What do we know what Planck's constant is? 6.63 times 10 to the negative 34. That's the value we obviously want to get to practical. We probably won't get that. Quantum physics, done. Or should I say the first the first subtopic in the topic in the textbook, done. Now guys, thank you very much for watching. We got to add an outro. To make this presentation, it took me 2 hours, and actually it took me about 4 attempts to record. About 4 attempts. This is my first recording, so cut some slack. Anyways, if I manage to help you, can you help me, please? Can you just assist me? I don't know what I'm doing. It's like it's going to be a hell of a long journey, but we're going to try and get every single topic out there.